In this video, we're going to learn about infinite series. An infinite series is a series with an infinite number of terms, which I'm thinking you probably could have guessed, but now we have an explicit definition for it. And if you want to see an example, there's two different ways you can write it, so we can have 1 plus 2 plus 3 plus 4, or whatever your terms are, and then ... it just goes on to infinity, and there's a couple of variations on that we'll see later, but so you can have the series written out, or you can have the formula for the series where we're going from 1 to infinity, and then sometimes if they don't, if it's an infinite series, they might not even put the upper and lower bounds because that just sort of implies that it's going to infinity. The next important thing about an infinite series is that sometimes they have a sum. So first, if we look at a not infinite series, this one only has 4 terms in it, so it goes from n equals 1 to n equals 4. And then we can add that together pretty easily. You can type it in your calculator, you can do fractions by hand, whatever, and you get 15/8. There's a general formula for this that has a pretty interesting history, and if you ask me in class, I'm sure I will tell you the story, but it's about a little 10-year-old named Gauss. So if we add up numbers from 1 to n, this is the formula for that, and we're going to use this later on in the video too. Not that you need to memorize this one, it's just kind of a famous one in math circles. Alright, so not infinite series, it stops at a certain point. An infinite series, it starts off the same, but see, plus ... So it keeps on going from 0 to infinity in this case, or from 1 to infinity, depending on your series. And then if we write the general formula, this is 1 over 2 to the n. And remember that this is a summation, so because we're adding all of these together, we really would like to know what is that sum. Alright, and in order to find that sum, we can use what we call partial sums. So a partial sum is the sum of part of an infinite series. Hence the name partial sum. So this is what we do. We have our series right here. And the partial sum, s sub 1, is just the first term, right? S sub 1. S sub 2 is the first two terms added together. So 1 plus 1 and a half, or 1 plus a half gives us 1 and a half. You could write this as 3 halves if you want to. That's what we're going to do in a couple of slides. S sub 3 is the sum of the first 3 terms. And then instead of writing out the first 3 terms, you could also do it like this. So S sub 4, I know that I have the first 3 terms, which is the same thing as S sub 3. And then I add in the 4th term. So really it's this sum that I've already found plus 1 more 8. So that's our partial sum for 4, and then our partial sum for 5 is really the same thing as everything that I had for S sub 4 plus the 5th term, and so on and so on. And the cool thing is that I can take all of those partial sums and put them in a sequence, and remember, a sequence is like a series, except you're just listing them, you're not adding them together. So I have my partial sum 1, 2, and 3, etc., etc., and because it's an infinite series, I have an infinite number of partial sums. Alright, now, here is the really neat thing. If you take the limit of those partial sums, then that is equal to the sum of the infinite series. This is a huge idea right here, so make sure you write this part down. That's super important. Alright, so here's our example. We have, from the previous slide, where we're doing 1 plus 1 half plus 1/4. This was S sub 1, S sub 2, S sub 3, S sub 4, S sub 5. So we can see we started at 1, and if you graph these, it's kind of asymptotically approaching 2. So the limit, which we're going to show this much better on the next slide, but for now just trust me that it's asymptotically approaching 2. So that means the limit as n gets towards infinity, n being the number of terms that we're using in our partial sum. So as the limit of s of n as n goes towards infinity, as that happens, then it's equal to 2, so that means that when we add this series, this infinite series together, it's equal to 2. It's not getting close to 2, it is equal to 2. Alright, so like I said, we need to find a much more solid way than looking at the sequence and saying, like, well, it looks like it's approaching 2. So, since we're dealing with limits, we know how to find limits. That's what we did on the very first day of class. So, if we have a formula, it's really easy to take a limit. So, same series again. This is what my series looks like. But this general term here, 1 over 2 to the n minus 1, that is not the formula for my partial sums. So I need to look at my sequence of partial sums, and here I have them written as fractions because that makes it a little bit easier to find the formula. So this was 1, 1.5, etc., etc., etc. Figuring out the general term, the top I see I've got 1, 3, 7, and 15, and I noticed that if I had 1, 4, 8, 16, like those are familiar, those are powers of 2, so I have 2 to the n, but I'm 1 less than each power of 2, so it's 2 to the n minus 1. On the bottom, I have powers of 2, 2 to the 0, 2 to the first, 2 to the second, 2 to the third, but I want to start at n equals 1, for this because I feel like it. So that means that I have to do 2 to the n minus 1 so that I can get this 2 to the 0 right here for the first term. Alright, so my general term is this. And then to find the sum, to figure out what is this equal to, I can take the limit of this general term. So the limit of the general term, if I plug in infinity for those n's, I get infinity over infinity, which means I can do L'Hopital's. So I take the derivative of the top and the derivative of the bottom. The natural logs cancel out, and then I have 2 to the n over 2 to the n minus 1. So really, like 2 to the n cancels out, and I have 1 over 2 to the negative 1 from this part, 2 to the negative 1. And then 2 to the negative 1, the 2 to the negative 1 goes up to the top, and it's just 2. So the limit, this limit, is equal to 2, which means that the sum is equal to 2. And we're not going to look a whole lot at finding sums right now. That's going to be something that we do later on, but just to get that idea of that's how you find the sum of the series. However, the problem is that not every infinite series has a sum. So for instance, this one, we're going from 1 to infinity of just n, which means we have 1 plus 2 plus 3 plus 4, etc., etc. And some places I know you'll see that this is equal to negative 1 over 12, but disregard that for now, please. Alright, so our partial sum, S1 is 1, S sub 2 is the first two terms, so that's 3, S sub 3 is the first 3, which is 6, and so on. So we get 1, 3, 6, 10, 15, 21. And that formula that I mentioned earlier that Gauss came up with, that's what our general term is for this. Or you can test it and come up with a formula, but just this is what that general term is. So we find the limit of this general term that describes this sequence, and I distributed the n to make it a little bit easier to find. So since we're going towards infinity, we can kind of ignore the plus n because it's so little compared to n squared. And then we just get n squared over 2. When we plug in infinity, we just get infinity over 2, or just infinity. So that means that this sum is equal to infinity, which is not a finite number, so it really doesn't have a sum because it just keeps getting bigger and bigger. So we have two choices for an infinite series. Our infinite series can converge. This is a big term, so make sure we know the word converge. Converge means that it has a sum, or the limit as n approaches infinity of the partial sums exists, and not only does it exist, but it is also finite, which means it's a number, or not infinity. So it can converge or it can diverge, which means that it does not have a sum, and the way that we know that it doesn't have a sum is that the limit of the partial sums does not exist or it is infinite. So if you get something weird for your limit, then it probably diverges. And those are the only two options. Infinite series either converges or diverges. And there are different types of converging, but for right now, we just need to know that it converges or diverges. And we really like it when a series converges because then we can do things with it. So if a series converges, then we can multiply it by a constant. Like if I have some random series, this is just a general series, if that series converges to A, and then I multiply that series by this constant C, then I know that the sum is still A, but multiplied by whatever that constant was. So that's helpful, and we'll use these facts later on, so for right now, just write them down. The other thing that we can do with converging series is that we can add or subtract them. So if I have two series that converge, like so this general one here converges to A, and then this general one over here sums to B, then when we add those two series, and we're still going from 1 to infinity, but we're adding these together, then really what we can do is we can take their sums, so A and B, and just add them together because we added the two series together. So the big question, apparently we really like converging series because we can do a lot with them, but if a series converges, will we always be able to find the sum? And the answer to that is no. But it's okay because we can still find out if a series converges even if we can't find the sum. So that's what we're going to spend most of this unit doing, just figuring out does a series converge or diverge. And there are lots and lots of ways to do that. If you can find the sum, then you know it has to converge, but that's not the only way to see that it converges. So we will talk about those ways starting with the next video. Bum bum bum.